study A2. So just a little background there and in how we're structured, that we have a local Australian panel, as well as the current activities and work of Study Committee A2, the international group that would have a representative, typically from each country, that's C-grade membership in a local region. All right, so the technical brochure 445 was again product of the work of this working group A234, a guide on transformer maintenance. Quite fortunate to have such a document. I wished I had such a document when I started my work with power transformers, especially asset management and maintenance and service of power transformers. So I regard this document as a useful document to have on your bookshelf for quick and easy reference. And you'll see through the document there are a number of references, further reading, to a much deeper study of some of the topics in the brochure. See there the working group members, a large membership there. Claude Rajot with Hydro-Quebec, and Claude is also the current chairman of Study Committee A2, very capable engineer and manager. So you'll have a working group usually divided up into task forces, so you have task force leaders at the top and the general membership below. It was in February 2011. The outline of the brochure, we have those chapter titles there. I'll use this slide throughout the presentation to move on to the next chapter that's been covered in this tutorial. So an introduction to maintenance. Created basically for newcomers to transformer maintenance, for asset owners, for young engineers, for technicians and service personnel interested in the topic to read really a very broad topic, transformer maintenance. It was really needing to contain how much material we were having to collect in this brochure. We could have had quite a greater, large document had we had time, and but also if we had not condensed it somewhat in the editorial. And where my main involvement was doing the editorial review, clearly a lot of internal writers, and not necessarily always with English as their first language, so it was quite a challenge to learn some of the terminology into what regard, I think, as global English. Hopefully you'll find it quite a readable document. So C-grade in the A2 Study Committee, their charter is to look at transformers, power transformers rated 69 kV and above, larger than 25 MVA. So I put there just to give you the relevance of this document is more medium and large power transformers. Throughout the brochure you'll see very useful diagrams like this. And this diagram really tries to into a flow chart what the transformer operation and maintenance cycle looks like. Clear the top, commissioning a new transformer, putting the transformer into transformer operation. Have below that the large rectangle surrounded by which is a broken line rectangle surrounding those four elements of maintenance strategy. So see the acronyms there and what they are in wording at bottom right. Now, time-based condition monitoring, one on the left, feeds condition-based maintenance, as does online condition monitoring. So that's deliberate that we don't do condition-based maintenance without having done some condition monitoring. To the far right, in that rectangle, we see time-based maintenance, the most basic form of maintenance strategy. And the outcomes from these activities is more information on the condition of the transformer. Condition assessment is it becomes a decision: are things normal or not with the power transformer? If they're all okay, we return the transformer to normal operation, continued operation. The transformer is believed to have issues, to have faults, to have degradation of some form. We don't really jump into a maintenance. Usually there's further interpretation. And data that we're relying upon for action, but also sometimes further interpretation, maybe extra special tests, or even some online monitoring, intensive monitoring of the transformer to evaluate just how critical things are, maybe to narrow the cause of the problem to a particular area on the transformer. And of course that could return to normal continued transformer operation. Usually through that interpretation we identify whether we have minor work or major work. We return the service after having done some corrective maintenance, basic corrective maintenance, and a few tests and checks. See that right there, the minor work and pathway. However, when it comes to major work, because of the expense of major work, because of the intrusive nature of major work, there's that economic evaluation done before spending a lot of money on a power transformer. And it may be that we scrap and replace the transformer rather than do refurbishment or repair on the transformer. So that's obvious or logical or straightforward expression of the transformer maintenance cycle. And delve into the next chapter, maintenance strategy. Maintenance. Well, to understand what is happening inside a transformer, this was prepared, this list of possible impacts on the transformer when no maintenance is done on the transformer. What could happen? So down the left-hand side you see a very intensive life cycle for the transformer, from new to 100% of its life used. And typically we see these sorts of issues listed in the main box in the centre there that can develop, degrade in the transformer. Some of these things are, of course, external, like paint, system corrosion, weathering, affected cabling, UV. Okay, I'll continue on. The way that oil leaks manifest in transformer often can be a driver for a lot of asset owners to act just on the observation that the transformer is badly leaking oil. I mean, if not being anything previously, sometimes it's not that having to top up the transformer to avoid the low oil level alarm that will start acting just to something to avoid the well situation. And gaskets and seals have a lifetime, and that's common with a number of parts of the transformer. Some of the tank fittings, some of the important components like the fittings and the tap changer are subject to wear or through degradation or moisture ingress, are compromised and fail catastrophically or with massive failure of the transformer. So we can start to see that with all of these mechanisms at play, with these typical modes of degradation, deterioration, or modes of failure, that some units, the units to critical units, there must be a large degree of impact when they do fail. So it really boils down to, I think, in a lot of organisations, deciding on what is your appetite for risk with your assets and how much you spend on them. I mean, if you take the typical distribution transformer, very relatively low value assets compared to a large power transformer, utilities make the conscious decision to no maintenance, and the maintenance strategy would simply be replaced after run to failure. So you'll see utilities have workshops with stock of new transformers, whole transformers, kiosk transformers, and instead of doing testing and or surveillance of these units, large in these units in the distribution utility, they would act the transformer actually fails. So for some devices, maintenance is a conscious strategy. But if you had a large generator transformer, your supply power to earn revenue from delivering power to the network, it's kind of stuck in a dramatic way when the power transformer, a generator transformer, fails, and it will take a long time to replace these large units, typically 7 to 12 months for the very large generator transformer to be specified or managed to delivered, erected, and commissioned. So clearly, no maintenance is not an option for these critical transformers. Any questions?
Ross, question from Scott Lexon in the chat window. He's asking, to what extent should these recommendations be applied to transformers less than 69 kV or 25 MVA?
Say that the most common conditioning that's done on the power transformer or any transformer would be oil testing, especially dissolved gas analysis. So you'd do oil sampling and testing on nearly every transformer if you're concerned about knowing its true condition, its whether any incipient fault at play, active gassing inside the transformer. Now, if we had small sized transformers. Now the pole-mount transformers, 200 kV and a kiosk transformer. I thought that that's such a low value asset, and that usually there's contingency to switch around its failure. Will supply a suburb or in some major industrial customer. There's maybe maybe 2 or 3 other transformers in parallel, or providing another way of connecting the industrial load. It's really a question of do you have a contingency? Can you tolerate the time to replace the unit, and therefore it could be the idea of doing little or doing nothing. I think for most medium power transformers, some level of surveillance is done, some level of oil testing is done, because open the opportunity for planned interventions, a planned outage to intercept a problem. So, and questions for whoever raised that? Is that what you're looking for? Yeah, thanks. All right, moving on. I think we've exhausted discussion on that slide. And interesting point with condition-based is that its trigger is a change in condition. But you're not doing time-based maintenance because you have a prescribed maintenance interval to do your repetitive routine maintenance. Instead, you have the trigger of actual condition of the transformer to be the trigger for action. So this diagram I have is showing how the inherent weakness with condition-based maintenance in that you need as for intercepting failure. So on this graph you see good condition at that level, at that good line plateau down to the left, and in time we get to X, and in concept we have some degradation, deterioration or change in this parameter. It diminishes. It's like everything that we make, everything that is retained or reduced, there is the law of thermodynamics that says that it will change from a state of order to a state of disorder. It will degrade, deteriorate. It's unstoppable, and so this is no different in the power transformer, whether we're talking about the oil, the population, the heat on the tank, you name it. It will degrade. It's just a question of will the component be part of the transformer degrading lead to some deteriorated state that we have a point of failure at Z. And so if we wanted to intercept that failure, we need to detect the change. So that drop from X to Y, a discernible change in parameter, would have to be detected by the transducer, detected by the test, detected by the visual inspection. And any one of those sorts of things that enough to detect change of state, but it needs to be timely, and it must, having detected that change, still allow you that time T, delta T, from Y to Z. It must allow you still some time to intervention to act before failure actually occurs. So in deciding on condition-based maintenance, you need to have some clarity with the modes of failure, the modes of degradation and deterioration and transformer. Whether you are monitoring it in the right way, in a timely way, and whether having detected change, having a signal, an alarm, a report that says that things have changed, things need to be acted on, do you still have time to act and then the ultimate failure? So the idea that if you've got online monitoring, monitoring of the transformer, you're relying on discrete intervals of tests, visual inspections to pick up change, and so it's a bit a problem with the sampling rate, even with continuous monitoring, is that sampling the high optimal for detecting change before failure. Moving on. In the technical brochure, we have surveyed transmission companies and generation companies for what they were doing in this practice on their transformers. In Australia, it was interesting when I prepared a survey for our own industry, electrical industry, only transmission companies responded because of the transmission companies privatising or petition, even if they're a government business enterprise, still in a competitive environment, there was great reticence even to respond to a simple survey on their maintenance practices. Fortunately, we did get some generation company responses to the survey, so we do have a balance of transmission and generation responses. So clearly, from the findings of the survey, we have these points I've listed on the slide here. Great difference in the intervals for even the simple visit to the transformer. And of course, for a transmission company, that's understandable with the geographically remote assets. And for a generation company, where the engineering staff, the technical staff have units, probably walking past them every day, there's the opportunity, far greater opportunity to make those visits and inspections. Well, tests, sampling and testing, generally in accordance with the standards. So most tests are done on any particular oil sample, especially dissolved gas analysis. The majority of respondents used electrical tests on a condition-based trigger. In other words, they were using usually the oil tests to say that there's something amiss with the in assembly, and then the electrical testing. Different companies tended to, because of the major outages on the transformers, on the machines, and therefore on the generator transformers, tended to do the electrical testing on a basis and not necessarily condition-based criteria. So I think, but I'll leave that to look at the brochure. It's interesting to look at the survey responses there. Changes, quite in the frequency on those, but in reality we do have different taps. We have some new technologies that do to relax the what was traditionally time-based maintenance. The number of operations is to be regarded as time-based maintenance. being bigger for the work on that changer. So high G, high number of operations, means that the tap changer usually sees more regular servicing. Practices, maintenance practices, I should say, varied significantly between the utilities. One thing that did come from a CEDRE reliability survey now back to 1994, that the things that cause, the components of the transformer that cause expensive failure are usually bushings, the attachers, or the active part, the windings in the transformer. So there's a clear message from that reliability survey that there should be some effort in realising what causes expensive failure. Those three things, there should be some effort in monitoring of those things. When you think of the active part immersed in the oil testing, DGA is an extremely important monitoring technique. For condenser bushings, the possibility of online monitoring, one might have to tap continuously. But if you don't have that, then taking the risk identified from the reliability survey, there should be some effort in doing some electrical testing, especially about at least the midlife age on these bushings. Well, they are the moving part in the transformer. There is wear and tear, but there's also electrical arcing, wear on the contacts on the diverter switch, the part of the switch that makes and breaks the load current. So they do deserve understand that careful vision on how frequently should we be testing, or do we rely on online monitoring on the tap changes? Any questions on that? No. Right. Factors that can influence maintenance practice and efforts. Worth just quickly going down these dot points. The transformer characteristics and specifications. And the most important thing is, when you get a specification for a power transformer, what you ask for, what you specify. And you'll see in chapter 4, the next chapter, transformer component selection, as a bearing on your future maintenance effort. So a very important point. Transformer appropriately specified is its environment, its pollution and marine corrosion, typical examples going to affect its maintenance effort. Is the way it's loaded, is the harmonics that's dealing with going to affect, going to prematurely age the transformer. So important to understand how it will be operated, where it will be operated, and do we specify maintenance devices for the transformer. That's the second dot point, the quality of the components installed in the transformer. The required duty of the transformer, the environment which we've spoken of, the historical transformer failure rate, and failure types. So you'll learn from your history, from your business, in your region, in your network, what is that record for your transformer fleet, what are node failures in that network, has there been learning from those past failures, from early premature aging has there been some learning on how to deal with specifying the transformers or maintaining the transformers or changing maintenance strategy? Okay. Those documents are pretty well self-explanatory, so I'll move on. There's a question. I can't read the full line, so Kia, can you read that to me? It's didn't get the full question.
Yes, this is a question from Shiva Tejwani. Have you found in your experience that lightly loaded transformers require more maintenance coming out due to inefficiency?
Let's take it to an even further extreme. What about spare transformer? Often people think that the spare transformer, never in service, will be able to be put into service with risk. Is your cold spare transformer, if it can get access to moisture through breathing, it will absorb, sponge up the moisture. Really, cold transformer has to have water transfer from the oil to the paper insulation and develop quite a high moisture content if it can get access to that moisture. On the transformer, they have an anti-condensation heater. Rarely do the air trans have those anti-condensation heaters energized, so it is possible for condensation and corrosion to start in that unused spare transformer. So now look at the lightly loaded transformer. In terms of the tap changer, we can think of things like the resistors are selected to make the 75% loading on the transformer. In other words, they dimension their resistor value so that they minimize the contact wear on the contacts when 7% or 100% is on the transformer. So it is possible that the lightly loaded transformer, lightly loaded tap changer, will have enhanced contact arc corrosion because the non-optimal value for the transition resistors. That's one example of how you may think that the lightly loaded transformer will be okay, but in fact there are some issues for the on-load tap changer. I think the other point for the loaded, just like the spare transformer, is the possibility that running cold or cool, that it is possible for moisture to be, if it's a free breathing transformer, more really than if it's a hot transformer. So a hot transformer tends to throw moisture off the paper insulation into the oil, and if you were worried about moisture in a power transformer, very easy to make a determination for your hot transformer operating at up at normal temperature rises, moisture off the insulation, solid insulation, into the oil. So it's an easier transformer to modify just how wet it is because of the moisture you can see in the oil. But the cold transformer, the lightly loaded transformer, problem. Difficult to make these moisture estimations in the solid insulation when you're taking an oil sample from these relatively cold transformers, because the oil doesn't get loaded with the moisture the way the moisture equilibrium works between paper and oil. The moisture will be sitting in the paper insulation, and for moisture and oil, that it should always be done with the transformer hot. If you allow your transformer to cool down, yes, you will get a nice low moisture content, because the moisture has been absorbed back into the paper again. We just take 1,000 days to establish an equilibrium, but basically, if it's generally lightly loaded or sitting as a spare cold spare, yes, the moisture will be taken up by the paper predominantly. Does that answer your question? Some time-based monitoring intervals to see based on what we found in the survey, the maintenance strategy survey. We're doing on whether it's light activity, regular activity, or intensive activity, the frequency of simple transformer visit, the detailed visual inspection. It's so easy to perform those things, yet look at the spectrum of frequency that some of the asset owners are doing those simple visits and inspections. The DGA, well, if you considered how quickly some of the mechanisms develop into catastrophic failure, you'd have to wonder why are some companies relying on 2 yearly or even an annual oil sampling program. Certainly not enough to intercept catastrophic failure of a critical power transformer. Of course, on the other hand, there's the expense of the online monitoring, the online DGA. Not every transformer can have online monitoring of its dissolved gas content. So it boils down to these companies are looking at risk, looking at the criticality of the transformer, looking at the consequences of the loss of the transformer, and using that to decide on how much they spend, how intensive the maintenance activity will be. It's giving you an idea that people do look at whether they're using a large fleet or just a handful of critical transformers, and deciding how will do their monitoring, how much money will they spend, how much will the activity be. Right, so there's the definitions of what constituted light, intensive, and regular maintenance. I'll leave that to you read at your leisure later. Let's focus now on a little bit more on this condition-based maintenance. Let's take oil testing as an example. Now, top left, we have that a limit value has been exceeded for a particular oil test. So you can see the first column, vertical column of boxes, we have different oil tests discussed. I mean, if this particular oil test is affected, in other words, its limit value was exceeded, say for a breakdown voltage, would be in the next column the possible cause. Breakdown voltage, your oil sample put into a test cell with spheres, breakdown voltage measured across spheres in the test cell. If you're getting, say, 30 or 40 kV or even less than that as a breakdown voltage, you'd be quite concerned whether there's a load of particles in the oil or whether there's very high moisture. in the oil or both. And so you can see how breakdown voltage is coupled with water content test to determine whether it was moist or whether it was particles, the culprit. Moving across, horizontally across to the far right, the maintenance intervention, or maintenance action be considered because of that particular trigger to the left on the oil test, telling us that something is amiss, something has changed in the transformer. So, trigger, action, and action is the message that is consistent with when you look back at the maintenance life cycle. We look at condition-based maintenance. We see being triggered by condition monitoring. That's the oil test here. And we see condition assessment and interpretation carried out from the possible causes. And if no work or corrective maintenance involved, then we have these triggered, as you see in the side of the diagram. So getting the idea on how condition-based maintenance relies on a trigger. I pointed a little earlier, which this slide is reinforcing, that online monitoring simply means we did just what do we mean by online monitoring, and we realised that there's a distinction to be made between continuous online monitoring and what is generally online monitoring. Online monitoring to be any sort of monitoring we do when the transformer is online. Doesn't necessarily mean what the next refers to, and that is continuous monitoring with usually a clever device involved, transistors, maybe coupled with an intelligent electronic device, an IED, to do some interpretation for us. So with online monitoring, with the visually inspecting the transformer operating online, or taking an oil sample with the transformer online, we are taking snapshots of the transformer's condition, discrete intervals. These inspections are done, these oil sampling taken at discrete intervals. So importantly to remember, these are snapshots of the transformer's condition, and if we want a continuum, if we want timely monitoring, then we have to move to continuous online monitoring, carrying real-time data and trends. Very useful, powerful in trends in the change in state. Take dissolved gas analysis. We're able to have the gassing rate, how many parts per million per day is being generated by the gassing site. Tell us something about the severity of the gassing fault in the transformer. We had trending. Online monitoring can be coupled with these IEDs, and that turns them into very smart sensors or even smart systems. A number of transducers can get to the one IED, so we can be monitoring a number of attributes on the transformer: bushings, the tap changer, the temperatures, state of the cooling, and learn a lot about the important factors that might be understood to decide just a change in condition for the transformer. Power was expensive, especially on a large fleet of transformers. Oops. We'll repeat some of those points I just made. So, there are some pretty sophisticated monitoring technologies, and we bring these to bear. We invoke these sorts of more specialised, more esoteric monitoring systems. We'll have maybe one of a group of transformers fail in a particular way. We realise that there's a bit of a common mode failure, and we need to focus on that particular mode of failure. It may need specialised transducers to this online. And that stop point, partial discharge detection, whether that's electrical, acoustical, or UHF signals, it's probably one of the most complicated but very powerful techniques for trying to discern electrical failure, or rather the pre-breakdown phenomena before electrical failure. Keith, what was that?
Question for me. I wanted to know what's the cost of implementing some of these online monitoring technologies, and I guess at what point do we have a decent payback in terms of deferring transformer replacement?
Right. Actually, I'll go back to that. I think it's covered more in the brochure itself. Look at page 10 later. But I'll just quickly read with the points that for vision monitoring with transducers, it's to be technically justifiable and economically justifiable was the point that they made in condition monitoring. To be technically feasible, we've already looked at it, needs to be timely, and plus make an intervention to plan an outage to accept the actual failure. But for economics, which is more about your question, it's the costs of the failure mode that you're considering to monitor for. If it's the tap changer or the bushing or the active part, we've already seen in the reliability survey that these devices do cause expensive failures. And when they fail, they're a critical component. They can catastrophic failure. In case of bushings, even oil fire with total loss of the transformer, and maybe collateral with the nearby transformer, even powerhouse with the oil fire. So how far you go, it's looking at for a particular transformer, the critic of the transformer, the consequences of its failure, for that, and looking at for the system that you want to purchase, is it comprehensive enough to detect loads of expensive failure? Is it easily maintainable itself? You've got a maintenance cost for the monitoring system itself, let alone the transformer maintenance. The life of these devices, there are electronic devices. If you consider the life of chips and electronic equipment in a environmental electromagnetic fields, out situation relying on the IP rating of the housing and so on to protect from the elements. Consider costs of the device, how it will be protected, how it will be maintained. Then you have your system in place, the interfacing with it. how will you monitor the outputs? How will the information be transferred? Who will lead the alarms? Who will do the interpretation? There's costs, hidden costs with it. You see companies just want to trialing, having systems, and work out, having bought them, all of the incidental costs involved with them when they find that they have to house them correctly, maintain them after 5-10 years, have to upgrade software upgrades because the supplier changing the software because of development problems or with improvements or upgrades in the software. It's expensive exercise. It does need careful thought about the total costs and how will you interface with it. How will it factor into things like your maintenance management system, maintenance planning, in your maintenance strategy? Thank you. This process. So I've got half an hour to go, so I'm going to accelerate this a bit. In the maintenance process, I think it's fairly obvious. There's 5 steps. It's important from the top in planning your maintenance effort, analysing for your maintenance, the actual execution of maintenance, and maintenance records, feeding back and analysing based on the maintenance history, the maintenance records, the maintenance will be needed on other units or on this particular unit. What's been done before needs to be known. Is there a mode failure in a group of transformers? This sort of thing is part of the optimization step. But I'll just give you a flavour for this section. We're looking at those 5 boxes very quickly. In maintenance planning, we have a saying in our business: plan to fail. And it's very much a gift. If you don't plan well, you don't prepare, you don't have all the resources, all the parts, all of the equipment that need in a planned outage. Outages are hard to get, to plan for, to get access to the transformer. So a great deal of preparations needed. Quentin, please, care.
The question is from Beer. What is the best approach to deal with corrosive sulfur in 132 to 33 kV power transformers? Question is in relation to a distribution network with 500 such power transformers.
Right. Well, I'll come into that very briefly, but firstly, there is another technical brochure, 378 from memory, C-grade, that gives you good guidance on the sulfur problem with many copper sulfide in mind. However, there is also the problem of forming silver sulfide on tap changes. And so if I was concerned about corrosive sulfur, I'd be concerned for the larger power transformers, those that have high operating temperatures, or especially generator transformers or maybe reactors that are on high load factor. Because the copper sulfide forms when typical transformer is hot or in hot parts of the power transformer. And it was associated with a particular additive to oil, DBDS, a disulfide inhibitor added to the oils intended to improve its oxidation stability, but unfortunately it introduced a corrosive sulfur problem. So there's a period of time, early 90s, when a particular company, because we're not in Secretary, we're not supposed to advertise companies or put ill words on particular companies, but suffice to say that the corrosive sulfur problem was identified with this problem with particular oil, a particular oil company adding this inhibitor. But in reality, sulfur can be in oil mechanisms. After all, sulfur is commonly in the oil stock that the oils are refined from, so you can still have sulfur species in the oil that hasn't been refined properly in the first place, let alone have sulfur added like an inhibitor in the case of this particular oil company, or maybe it's the sulfur from vulcanized gaskets, your elastomers can introduce sulfur to the oil, or a contaminant. Like oil can be contaminated in many ways, but maybe it's sulfur that's introduced as the contaminant in the contamination of the transformer oil. So if we're concerned about corrosive sulfur, we need to be thinking of those groups of transformers that we think may be at high risk because of their high operating temperatures, the fact they have the low oxygen oil preservation system was another factor identified to be to creating the copper sulfide in the insulation, but also the transformer have a tap changer with silver coated contacts or bushing connection parts or connectors somewhere in the transformer that are silver plated would produce silver sulfide, and the silver sulfide, when it does form, it likes to flake off again. It actually flakes off in very large flakes. So high danger to certain transformers. So if we were to monitor this, we'd take an oil sample, we'd do the corrosive sulfur test for copper sulfide, but we should now also be adding the DIN standard, DIN 153, DIN 51513, I think it is, for the silver strip test to see if it will actually tarnish silver and form silver sulfide. It's probably enough on that topic that we can afford at the moment, but have a look at technical brochure 378 for further reading. So, system, and that's where the maintenance reporting factors into the maintenance management system as well, but in the context of planning, the large utilities, transmission companies, distribution companies usually use a maintenance management system, and so they do record all of these facets of the transformer fleet, in them plan and manage their maintenance effort. In Auckland, we make a big deal in the guide about the 5 levels of competency. For tasks, you do need, for basic things, level 1 level of competency. But as you get into guidelines and procedures, complex procedures, complex tools, then you need higher levels of training and competency in staff who are performing work, through to levels 4 and 5, where you're starting to use your extremely experienced supervisors or your technical experts to assist in the work and managing, overseeing the work and interpreting tests and deciding on appropriate modifications or changes in the power transformer for on-site repair. In execution, we make some interesting comments on both the safety of people but also the safety for the transformer. Reading that, and in maintenance records, so often I see electrical tests done or oil samples taken on the transformer and not enough information recorded. The conditions of the day, was it raining, what was the temperature, the ambient temperature, what was the operating temperature of the transformer in the case of an oil sample being taken, what was the load on the transformer. For electrical tests, the temperature of the transformer insulation, granted it's offline, has cooled down, but still, depending on ambient and if the transformer is still cooling down, the temperature of the insulation affects the result of the test. Take your basic winding resistance. Copper will have higher part of the copper. Insulation resistance, the electrical test, the humble mega test of insulation resistance will drop with increase in ignition temperature. So you can see why it's important to keep good records to help in assisting just the interpretation of the test. In optimization, there's a bit of discussion in the guide about reliability-centered maintenance. It's really a basic way we implement reliability-centered maintenance when we talk about applying that to power transformers. It's not your classic RCM you might see with industrial processes. It's more about identifying risks for the transformer, the failure consequence and the likelihood of failure in deciding your maintenance effort. It's in combinations of time-based maintenance, time-based condition monitoring, condition-based maintenance and online condition monitoring, using an appropriate mix to affect economic component selection and maintenance. Big chapter in the brochure, and it really is making some interesting observations on some of the important components of the transformer that your future maintenance effort could very well be determined by units you select, the quality of them, the type of them, the features in them, the maintenance effort required for them. They vary with different techniques, different types. So we do have a good discussion on advantages and disadvantages of different components. So an example is the oil impregnated paper bushings, condenser bushing. It will take us straight out of the guide on the advantages and disadvantages of this particular type of bushing. It's well recognised that the OIP bushing, when it does fail, shatters the porcelain envelope, tends to drop the condenser core into the tank, drop into the transformer. So you've got an arc, an oil arc started. With failure of the bushing, you're now dropping this arcing oil fire into the transformer. You'll have oil under head pressure from the conservator going from the opening where the flange of the pin past this burning core. And so straight away you've got a oil fire triggered. So it has, when it does fail, it has high risk of a resultant transformer fire. Total loss of the transformer possible. So it's been recognised that the resin-impregnated paper bushing has a distinct advantage over the OIP bushing. Something to be considered when there's critical asset or nearby assets at risk for a major oil fire. There's the advantages and disadvantages of the resin-impregnated paper bushing coming next, and its advantage, a non-flammable core, less likely to be affected by water ingress when it's mounted in the transformer. So as you see in the disadvantages to the right, the oil end of the can be protected from moisture during storage. So less affected by water ingress mounted in situ in the transformer. They're quite vulnerable to moisture, not protected on its exposed oil ends in storage. It's really about giving you some useful features, some useful of considerations, typical treatment of considerations, and inviting you to read further. The technical brochure is not meant, the tutorial is not meant to capture everything in the guide. It's a very large document. So, useful illustrations here. We see the different ways that a condenser bushing could be connected. So you do have to be careful in understanding your condenser bushing. How is the line lead connected into the bushing? How are you to remove the bushing? If first you don't study the manual, the type of bushing fit in the transformer, and read how should the bushing be disconnected if it is removed from the transformer. And there's a long list there of components of a power transformer covered in this component selection guide. Well working. A quarter of an hour to go, and the next big chapter is this maintenance action catalogue. And you'll see, as I flip here, the darts. We take electrical tests and DGA, our important diagnostics when we are concerned that there is something wrong with the transformer, especially say if the transformer has produced an alarm or has just tripped. We hacked the protection, decided that it is a genuine problem in the transformer, and it's useful to consider this diagram here to show what are the various basic and advanced electrical tests that can be done. Together, dissolved gas analysis on the bottom row at the bottom of the diagram. What do they tell us about the transformer? What types of problems are these tests useful for detecting? So I've highlighted in red, just as an example, the red font, frequency response analysis. And if you with those 4 red dots, that FRA is good for detecting winding turn-to-turn issues because of the disturbance in the winding structure. The winding geometry for changes in the physical demanding, whether it's collapsed, whether it's buckled, distorted. FRA is very sensitive. You'll see a change in the signature, especially between the 1 kilohertz to the 1 megahertz. You'll see changes in that band of frequencies if in either winding to winding geometry change, in part of the frequency spectrum, say 1 kilohertz to kilohertz. You'll probably see changes in that band for winding to winding geometry changes. In other words, uplift, distortion, collapse. Or we have within the winding changes, in other words, buckling, torsion to this structure, changes the series capacitance, the shunt capacitance, but more importantly, the series capacitance of the winding. You can see that in the tens of kilohertz through to 1 megahertz frequencies. So the other 2 dot points, the magnetic circuit insulation and the magnetic circuit integrity. See that in the less than 1 kilohertz, that resonance, deep anti-resonance, that's that spike on the roof, due to the way core affects the signature. The red curve, if there's, say, a short on the core, or there's a core problem, that anti-resonance disappears, you see, in the red trace. So bring up the magnetic circuit problem in the red trace with that anti-resonance for some reason and not being present any longer. So you're getting to see how we use the tests, being of course, with experience, familiar with how the tests are sensitive to particular problems. Start to learn more about interpretation of them, more about the transformer. So the test is treated in this way, in a table like this. The detectable failures that are typically why we use this particular test in detecting these types of failures was the way the indication may be showing up in DGA in this case, or high internal temperatures. That might be the indication in the transformer why we would now invoke winding resistance tests to tell us more about what's amiss in the or the connections of the transformer. Methods discussed. In other words, what other information do we need together with the electrical test to interpret the test? A little bit of discussion on interpretation of the test and some further comments on the test. So some useful reading if you're new to some of these electrical tests. Dissolved gas analysis. I encourage you to go to that section and read the further reading, interpretation of dissolved gas analysis. I think if each and every one of you are involved in our transformers and need to learn about incipient faults, gassing in transformers, and how to interpret the gases that are detected in the oil of an oil sample. You need to look at these interpretation standards. There's IEC standards and there's IEEE standards. Both are useful to learn more about getting a better feel for interpreting the relative levels of gases It's so dependent on the energy of the fault in the transformer. Such a complex thing, the oil molecule, depending on what temperature fault is, what energy is involved in the fault, you will see different proportions of the gases determined solely by the severity of the fault, the temperature of the fault. Very interesting. In general, we have 3 groups of tests. Group 1 is probably the ones that you'll be more like to experience or to look at results for, to interpret in your work with power transformers. Groups 2 and 3 are more to do with selecting appropriate oils, as in oil, or the condition of the oil with reclamation, or whether it's a particular inhibited oil or passivated oil, meaning its performance. And group 3, corrosive sulfur and PCB. That's usually because there's a contaminant, additive affecting the oil. So that's why they're grouped separately, group 3. Useful diagram here, transformer problem across the top. 3 typical problems we have in transformers: overheating of the transformer, discharge, low energy sparking in the insulation or the electrodes of the geometry of the transformer, hydrogen gassing typically, and right damage to the hermetic seal, in other words, allowing moisture ingress. We can see a number of oil parameters down that far left column, and the table gives you less high influence from that transformer problem causing in the oil parameter question, or M for medium influence, or L for low influence. So you can see which tests are influenced more by a particular problem, and you'll see a 1, 2, 3 through to 12 different factors that in a particular test. So it's quite a useful diagram to quick up speed with what's useful, detecting what sort of problem, and what's the sensitivity of that test to a particular transformer problem. Useful table. Change of tests. We have this diagram for two types of transformer: tap changer, back resistor. You need to familiarize yourselves with different types of tap changers, but the most common one is the high-speed resistor type that we typically use here in Australia. And the diagnostic methods: vibroacoustic, motor torque, DGA, IR thermography, dynamic resistance. For different problems, listed down that left-hand column at the bottom, which diagnostic method is good, X, or maybe of low or moderate use in detecting the particular problem in a particular type of tap changer. So for us, we'd focus more on the resistor OLTC types and see that for vibroacoustic, let's take that as an example, the diagnostic method, signature of the ultrasonic microphones, pretty sure, used to detect the vibroacoustic signal from the body of the tap changer. But if we have problems with linkage and gears, we have good sensitivity to that problem with vibroacoustics. What is ease? It's good for timing and sequence issues, for contact wear and transition resistant problems. Transition in the tap change itself, when the inverter operates. So useful charts, useful diagrams, all in this brochure. Right, 5 minutes to go. I'm going to rush ahead just to get the most important points. What's left. Dry, the typical site dryer set up in the photo there. Lagging to keep the transformer hot. Pump shrouded under that blue tarp, connected with a large bore vacuum hose and vacuum valve attached to the turret. So it's a field dryer being conducted because the transformer was of high likely moisture content that it warranted a field dryer. We now have alternative of online drying, oil drying, but that would only slowly dry a transformer, and we see some comparisons of different drying techniques in the next slide. On oil dryers, the molecular sieve, what I'm referring to, is being useful for moderate or low moisture problems. When over 3% moisture in the paper, we should consider the need for an on-site dryer, because we need to quickly reset and efficiently dry the transformer quickly. The molecular sieve, the online dryer, is a very slow process. Oil reclamation is considered when you have poor oil quality. So when oil gets oxidized, it produces the acids that will attack the paper, and so it's not just heat, but it's also the oxidized oil and its acids that will deplete, lower the degree of polymerization, the indicator we use to show the aging of paper insulation. As the paper ages, its degree of polymerization reduces, and it loses its tensile strength. So polymerization is correlated with loss of tensile strength in the paper. So if the paper weakens, it's less able to withstand through short circuit faults. The more likely that there'll be tearing, rupture of paper insulation, that a disc-to-disc, turn-to-turn fault may occur in the windings because of the mechanical weakening of the paper. So in the guide, why we invoke some of this major work. There's discussion on here in this slide the precautions for that invasive work. We take intrusive work lightly. It is costly to implement. There's a lot of preparation required, and there's a lot of care needed, and the competencies and experience are needed for carrying out intrusive, invasive work. So 12:30, I just want to quickly say it's useful to go to the major work section, that last chapter of the guide, to look at the sorts of economic decisions that are made, the evaluations that are made in deciding whether to carry out a major repair. Is the decision, should it be done on-site or in a workshop? There's the questions of transport of transformer, if we decide to send it away to a workshop. There's the comparison of what new unit cost, what would a new unit introduce if we decide new technology transformer, lower losses in the iron loss and the copper loss. Would that be a consideration in the overall costs of the exercise? You'll see some nice examples very interesting to see what was in the mix, in the balance of costs to decide on-site repair versus off-site repair versus replacement. Very interesting area for the guide to read. After major work, we need to consider what what testing we should do after the repair. There's some discussion there on recommended tests depending on the amount of modification, the amount of change that's occurred in the transformer. You may decide on going to some very sophisticated testing after a repair. That graph there just gives you a useful how core decline, watts per kilogram loss, and core steel has declined with improvements of core steel. So it may be that for a very old transformer, you just in the improved core loss, that may tip its favour by a new transformer just on the loss reduction with the new transformer. So I should quick chance to ask any questions now at the end of our allocated time. Happy to take question email in your leisure later.
We have one question from Michael.
Yes.
He's asked, does the impedance of the transformer change in value over time, or following a high fault current flowing through the winding?
Right. A change in impedance would be associated with major movement in the windings or collapse in windings. So you should already see some significant changes in the frequency response as well. If you discern a change in the leakage reactance, so single-phase leakage reactance is the test normally done to discern change in the impedance, and you would do a comparison of A, B, and C phase. So if there's been a collapse after a major circuit fault, major through fault in the transformer. In other words, if you've had the transformer trip offline, there's been a short circuit fault involved, you know that it's had been subjected to very high through current, then electrical tests would include single-phase leakage reactance and FRA, as well as some other electrical tests to decide on whether the transformer suffered. An internal inspection is warranted. I think you mean change in impedance through something happening to the transformer, correct?
Yeah, correct. Just wanted to find out.
Well,
thanks for that.
Always that sensitive, but yeah, when there's major changes in the geometry, it can be changed. Yeah. Well, thanks for your attention, and I hope you'll enjoy reading it. It's quite a nice, readable document from the back I've got from those that have looked at it, give me some feedback on it. And what's nice about it is you've got lots of further reading and references sprinkled right through the document. A good document for a reference on your bookshelf, I believe. There? So no further questions?
Thank you. Thanks. I really appreciate your time today.
Thanks for supporting with hosting this.
Thanks, Ross.
All right. Thanks, everyone. Bye.